Hi, so Zora. I'm currently a second-year PhD student at Carnegie Mellon University in US. So my research interest is mostly based on code generation. So like that could be mainly two branches. One is using code to solve like programming tasks, like repository level code generation or leak code style programming tasks. But also another thread is using code generation to solve more realistic tasks that people do in everyday lives, such as web navigation, solving math problems, or question answering problems, everything that you can solve by just generating the program. So the work that I'm going to present today, agent workflow memory, is more on the second thread, where agent basically generates code and you could do digital tasks like web navigation. And um, yeah, so I'll get started. So this agent workflow memory work is the joint work with both of my advisors, Daniel Fried and Grant Mubick, as well as Diane from MIT, who's really had a lot of experience in robotics skill learning. Very happy to do this project together with them. So yeah, that's sort of the motivation of this talk. So agents, for now, one of the biggest challenges is that they struggle with complex long horizon tasks. So for example, here, an example, this is what I extracted from the WebArena, what the data sets that we'll talk about later, that this is an example instruction. It's create a repository named this, and that includes a README file with the link to the most active 6 DIY ideas on DIY subreddit. So this is a very lengthy instruction, and it involves a lot of like multiple steps of very complex steps to solve this one. And so imagine if you want an agent to learn to do this task, it's very hard to like generate or annotate correct data that can help model effectively learn this very complex task. Because one way to understand this, you can dissect this task into several subtasks. One is create a repository with this name, and then second is to add a README file to the repository. And the third is to find the 6 most active ideas on DIY subreddit. And you can compose very complex long horizon tasks by composing this similar subtasks in various ways. And that could cause the space of long horizon tasks to explode, sometimes exponentially. So it's very hard to enumerate all the possible training data on this possible combinations and effectively train agents on that. So that's one of the motivation for our workflow is we call this each of the subtasks a workflow, and the workflow for imagine this entire instructions on the example level, and this create a repository or create a file task is a workflow. The key difference is that this workflows appear multiple times or can reappear frequently across different examples. So these are actually reusable subunits. Once the agent learns one of these workflows, and it can reapply it to multiple examples when it's involving it. So it also is similar, or at least personal to me, was similar to like how humans would abstract the workflows and learn skills is we don't exact our past experiences in the exact way that they appeared, but we do abstract out the like subroutines that you could sort of group them as the reoccurring task, and you memorize that workflow in your brain. And next time we experience a new task, you try to compose the various workflows you memorize and apply them to solve the future task. So that's more on the conceptual level, but also on the performance level, it's easier to collect data for training, and it could possibly generalize arbitrarily complex tasks. So with that motivation, we proposed this framework called agent workflow memory, which basically is to augment the agents with increasingly complex workflows. So this is the illustration of the overall pipeline. In the middle is the like basic setting of the agent. Need to have an agent and a memory. So for the agent, you usually have like a base memory, at least covering the primitive actions you'll use to complete the task. And also, most importantly, a language model backbone. So the model can provide heuristics and actually generate the actions. And the agent needs to solve a task in the environment. In this scenario of web navigation, the environment is the web page they are seeing, and the agent observes the environment and take action on the environment to change it or seek information from it. So the pipeline looks like given a user instruction such as who ordered this order, and we first gather some experiences from the agent, whether it could be from human annotations if we have ground truth data, or you could ask the language model or the agent itself to generate some experiences. We'll like discuss each of these variants in the next slide, which in different settings we use different ways to get these experiences. And having these experiences, another step that we do is to make sure that these experiences are correct. So we want to get positive data to make sure that the data are actually useful for agent training. And the most important step is step 3, which is inducing workflows from this experiences. So basically inducing those subroutine reusable workflows from um, concrete long trajectory examples. And I'm showing an example here, but I guess we have more if this is not clear enough. So for example, on the experience side, we have this concrete instruction asking who ordered order 0130, and then the agent clicks the orders button, then scroll for multiple times, and then finally send a message. And some reoccurring um, task maybe click the order link and return the message. So I can also explain that later, but two important properties we're asking for the generated workflows here is they induce the things in an abstract way. So they abstract out the context, example specific context to make the workflows more general. And after we have this reusable workflows, we integrate that into the agent memory. So the agent could leverage these workflows when generating future actions. So hope this will make the workflow induction part a little bit more clear. So about how we induce workflows, implementation wise, is not very complex. It's basically just prompting models. The input is the set of experiences or examples that you collected from human annotation or agent past experiences, and you input those to the model and ask it to generate a set of workflows. The example could look like this. So on the top right corner, when I'm showing this example, here is the natural language user instruction, and here is the list of actions the agent take to complete this instruction. And the model generates the 3 blocks that I put on the bottom of the page, and also like colored it correspondingly with the subroutine of the ground truth agent trajectory. So from this example, the agent generates 3 workflows, subroutines that could reappear across different tasks. One is called enter flight locations, where it basically enters the departure and destination places to fill in this information for the flight booking. And the second is if you want to select the date of your travel, especially in this case, the one-way date. So this could be another workflow. And the third is if you shop using your mouse, you can have this like click this button and submit it. So as this illustrated is basically you want to generate workflows that can cover some part of your examples. And together with this entire set of workflows, you want to cover as many actions possible in this entire example. Um, but in fact, we could have like multiple examples on the input side and multiple workflows on the output side. In a more ideal case, I didn't put all the examples here, but imagine you have multiple examples here and you want this blue like workflow block to appear multiple times in these examples and similarly for other workflows. So that would be an ideal case where we have like a well covered set of workflows to cover all the experiences. And so, as I said in when we're discussing the overall method, two requirements were, at least is that what we put in the model prompt, is to ask model generate workflows. One, that it's reusable sub-trajectory across these different examples. And second, we ask them to remove the example-specific context. So an example here would be, for example, the interflight locations the in the actual agent trajectory that actually enters Seattle and New York, which are concrete values that may not appear in other example. Imagine you might have another example that actually flies from like London to Pittsburgh. So what we do here in the workflows is we ask the model to replace it with a variable name. We replace Seattle with departure location or replace New York with destination location. So it generalizes to all the possible like values that you could assign to these different variables, and that has shown to be like beneficial, at least on the two data sets that we experimented with. So that's on the workflow generation. And here is like the two application scenarios of our agent workflow memory method. So this may make the first overall graph clearer. So the first setting we have is when we call it offline setting, is when additional examples are available, such as training data that you have annotated for that domain that you're testing on, where some collected human trajectories that you could use to benefit your testing. So assuming that we have some training examples that align with the distribution of your task examples, we can do this workflow induction and action generation in two phases. So in the first phase is we input all the training examples where you have ground truth annotation about the agent trajectory, and then you induce a lot of different workflows um, in this format, this like text abstract format that we just show, and then append all of these workflows to the agent memory. And then intermittently at inference time, you just take all these workflows into the memory and apply it to solve each of the task examples. I would say this is a pretty standard setting, like as you know, similar to the training and testing, but it does require additional examples available. And one like intuition that I have is, especially when the first agent data is not very easy to collect. Also, when the training examples does not perfectly align with your task examples, like the task distribution or the domain distribution is different, then this method may not give you the best performance. And that gives to our second scenario, which we call online scenario, which we don't require any additional examples. This is the scenario that I personally like better. So this has really like minimal requirement on data. You just need the task queries available and don't need any ground truth annotation. So basically, this in this online setting, we're asking the model to adapt itself based on its past experiences. And the way how it works is we pass the task examples one by one in the stream. And when we pass the example one, we ask model to do the induction, workflow induction, as I show in the last page. Then we augment, for example, we generate 3 workflows with the first example, and we augment these 3 workflows into the memory. And then we apply this 3 workflow augmented memory to solve the second example. And then the second example might give you 2 more workflows, and we integrate that. And now we have 5 workflows in the memory. And then we use those 5 workflows to solve the third example. It's actually building upon the past experiences that the agents have solved. But one thing to notice is we also have this trajectory evaluation step. So basically, here we first, given a query, we ask the agent to generate a trajectory that attempts to solve this query. But sometimes the agent can do it correctly, sometimes they cannot. So we also add a like language model based evaluation module to test to judge if the agent solved the query correctly, and only when the trajectory is predicted is correct, we ask the agent to induce workflows and then integrate those workflows into the agent memory. So in some way, it also depends on the agent's own ability to do some tasks correctly, or otherwise it's a bit hard to bootstrap this method to work increasingly better. So that's mostly on the method side. Any questions so far? If not, I can continue. Um, so now that will be our experience. We mostly test on web navigation tasks, and we not introduced, we used 2 datasets. One is called WebArena, and another is called Mind2Web. I think you probably are already familiar with that. So we'll go through them one by one. First is the WebArena. This is the like I think a data set that I really like about. It also is done by another senior PhD in my lab. But the basic setting of this WebArena, in case you're not familiar, is they have this 5 websites covering shopping or online forum or travel, these different domains. And the most important property is it has a rigorous functional correctness-based evaluation, so you can actually execute the model um, action prediction and tell if that agent actions are correct or not. But they do have some limitations on the data, is that they only have 812 task queries without any ground truth annotation for those task examples, nor some compatible training data. So this is like a direct dive in the results. Maybe it's better that I introduce these baselines first. So WebArena here, the WebArena, this line is the baseline result when they propose this benchmark. It's basically just prompting GPT-4 model without additional tricks. And this auto eval method is it asks the model to generate a feedback about its past action generations, and using that feedback as additional input to refine the actions further. And it improves over the pure vanilla prompting baseline a lot. And another set of baseline, which is the new framework called BrowserGym, it has updated the interface a bit. But I think compared to WebArena, the most important difference, they changed the action space a bit to include more primitive actions like hover or send message to user besides just clicking a type. And they also changed the input, the observation space of agents. For WebArena, it only includes the accessibility tree of the web page, and for BrowserGen, they use both accessibility tree and HTML. But also to ablate that, we also tried accessibility tree, input accessibility tree only using the BrowserGen framework. And lastly, there's this step method, which we sort of see as the canonical setting for our method. For their implementation, is basically they manually write 14 workflows, but actually they call it policy, but it means similar things. It's like a human reading canonical form of workflows, and they put that into the agent's memory, and they got pretty high results. And but in comparison, our framework got overall the total success rate we got it the highest, and then many of the this is the breakdown of each of the websites covered by WebArena, and at least on some websites we get it the best result. Um, but basically comparing to this open source frameworks, not open source, non-canonical frameworks, we always got higher results. But just comparing to the step method, they got some primitives on like some websites. And this is the first dimension that we evaluated, which is success rate, whether the agent can solve the task successfully. And another is the number of steps. So we measured this for like the methods that we have results access to, and especially compared to, I think comparing to the browser gem baseline, we have like a two-step reduction on average across all the tasks. And also comparing to the auto develop methods, the like a very significant drop. I guess because the auto develop method to take their method to work, they need to take additional steps to generate comments and refine. So it would take more steps. Overall, our method gives higher success rate on finishing the task and also can do it more efficiently. And okay, yeah, so another more on the efficiency side is we plot this accumulative success rate where we're doing the online approach on the WebArena examples, and we uh, observed something interesting that actually the success rate increases very rapidly in the beginning, about only like 40 examples. And then after that, the like 100-ish examples, the model just like gradually stabilizes to a very high success rate. And if you like enlarge this part, and this is actually a teaser figure of the paper, but this is a nice illustration of our method, I think. So this dark line is our method, and this blue line is the baseline method. Where the baseline, it increases a bit in the beginning because it started to do something correctly, but it didn't like continues to increase, and it just like stagnant here. But for our method, I also plotted this workflows. So these are actually based on illustration of the agent actual generation. They actually generate this workflows at this time steps. So basically, after a few examples, the model started to find or to generate a workflow that is relatively easy. For example, find a place by its name. And then later on, it may build on this to generate more complex workflows. For example, after you know how to find a place, you can further take another one or two steps to get the coordinates of the place, or also get a zip code of a place. So the future workflows also depends on the previous easier ones. And it's like again similar to how humans learn. You start from the easier skills and then gradually combining those easier skills with your experiences to build like more complex skills and then acquire them. So that's illustration on the efficiency side, and this is similar to what I just discussed, but we also did this cross-task generalization on WebArena. One caveat about the data creation is they actually first generate a bunch of templates and then instantiate these templates with different values to create examples. So this is a fake example, but it shows the mechanism. So template could look like show me like location, and this location is the like variable they can replace with different concrete values. And then the like when they are creating the examples, they just assign different values like Pittsburgh, London, New York, and create that as different examples. But one caveat is that imagine like our workflow method typically works well on this on examples have shared templates. So for example, if I have a workflow that can do show me Pittsburgh, then you can imagine it could already solve the other examples like show me London, show me New York. So that is not really challenging, and they may not. This kind of repetitive examples may not often appear in real time. So we're thinking just play out that part and see if our method can do cross task or cross template generalization. So basically, can a workflow for show me Pittsburgh generalize this to get the zip code of London? So what we do is we create a subset of WebArena that only cover one example from each template group, and we evaluate on this subset and also find that our method performs the best across different sets of methods. And the mechanism of how it's doing the cross-task generalization is basically that the agent learns to build more complex workflows from the earlier ones. This is an illustration of one example, easier to complex workflow. So to start with is find a place by its name, and it's just 2 steps to fill in the location name and click this submit button, and then to further get the zip code you might need. Another 1 or 2 steps to click the correct button, show the zip code, and then return this message to the user. So it's still like some part of the task is still sharing, but the model is learning to build in more complex ones. So that's mostly on the WebArena dataset. A brief recap: we got higher success rate and enables rapid learning with only tens of examples. We also did a cross-task generation task, and that also leads to the Mind2Web dataset, which emphasizes more on the generalization settings. They have this 3 task splits that targets 3 different cross generalization scenarios. One is cross-task generalization on the same, basically on the same website. The training data and the task data cover different tasks. For example, their training data, imagine you have this Amazon website. The training data may have an example of buying a product on Amazon, and a task example tasks apply to jobs on Amazon. So it's still on the same website, but the task trajectories can be pretty different. And the second split is cross website. So they actually test on different websites, but within the same domain. Say for training examples, you have shopping Amazon website, right? In test, you might have shopping and then Target, which is another grocery website in the US. And the third setting is cross domain. This is like a further gap. So in the training, you might have shopping Amazon, and in the task, you might have traveling United Airlines, something like that. And that's on the task coverage. And they do have like training data covering part of the tested domains and websites. But they don't exactly cover all of the possible tasks, the websites and domains as this in this 3 different task splits. So we can do a little bit of the generalization tasks. And they have a very good coverage on different tasks and websites. One slight drawback is their evaluation metrics is still based on lexical-based evaluation. So what they have is for each task, you have a fixed number of steps to complete that task. And for each step, you evaluate the element accuracy, basically have the model selected the correct element to operate on. And second, the action of one, is the model generate the correct action? And the third, if both element and action got correct, this step is correct. And then further, a level up on the entire task level, if all the steps are correct, then this task is correct. So that's the basic setting of Mind2Web. And we tried, because there are baselines using different models, we tried both GPT 3.5 and GPT 4. And our method is to be able to achieve the best result across these two models. And if you compare this to four columns, so actually you find the key for us to get higher success rates is actually the higher element selection accuracy. So, like, one, or at least our explanation for this is because we induce workflows in a way that abstract out the example-specific context, that we replace, say, New York by departure location. So when putting those abstract workflows into the context, the model is not prone to just copy the context or the values in the examples and just generate it. So the model is like forced to instantiate the value based on the current task. So in that way, the model may select the elements more accurately. But there's another dimension for the action selection, our method is actually slightly lower than baseline results. And our explanation for that is workflows actually introduces some bias on the next actions the model would take. Um, because the workflows usually includes multiple steps and the model is supposed to follow those steps. But sometimes some examples for this workflow may not apply to this example that are testing, but the model still just blindly follow that workflow. That may lead to some inaccurate actions generated at some steps. Um, yeah, so that's on a deep dive on these two dimensions. But overall, comparing to like Um, yeah, another thing that worth to mention is the synapse baseline that what they actually do is they actually retrieve top relevant examples and append them into context. So it's compare our method to the synapse method is really mostly comparing like the workflow format. Is it better to have a subroutine abstracted workflow, or is it better to have a context full trajectory examples? And from our results, it seems that like subroutine abstract workflows works better. And here's the generalization task, and we have some very interesting findings here. So for this generalization task, we do AWM offline, AWM online. So just a recap, offline is like you induce workflows from the training examples and then apply to solve the task examples. And for online, you don't need the training example at all. You just induce that while you're solving the task examples. Um, so like we also put a baseline here, but just to show, both versions of the EWM works better. And interestingly, comparing this offline online method, you see from left to right is like when the train task domain gap is gradually widened. So on cross task, it's just the tasks are slightly different, but the domain, the website is still the same. And then on cross website, you keep still in the same domain, but you're on different websites. And further on cross domain, you're just like doing tasks in a completely different domain. And we see that as the train test domain gap widens, the online methods gets better. So in the cross-tag setting, the offline still outperforms online a bit, and in cross-website they're like comparable. And lastly, in cross-domain, the online method appears to be better. It also aligns with our intuition that because online don't rely on any of the training data, it doesn't observe any gaps because there's just no train. So this online method could just generally generalize across different tasks and websites and domains, where the offline methods, still gets essential like help from the workflows induced from the training examples, but would be affected by the train task domain gaps a bit. So like maybe one practical implication here is if you have very like domain and task, if you have like a distribution aligned training set, with your task queries, then it might be better to like use the offline method here. But if you don't have any good annotated data, you might just try the online method. So that's the main experiments on the Mind2Web dataset. And also to recap a bit, we got also the state of the art results, and also we tried this cross-task, cross-website, and cross-domain generalization, and find the online version actually generates much better than the offline method. And lastly, there's more like ablation studies on like, especially in the beginning, we're designing the workflow representations. We're exploring a bit what is the best approach to represent these workflows. And we tried, specifically, we tried this two variants. One is for now, we're mostly representing workflows in code as they appear in the agent action trajectory. um, they were also wondering these models may be better at consuming text than programming languages sometimes. So we just translate this code format workflows into text format workflows, but basically just like verbalize it. So the code format may be click order ID, and then the text format may be just click the ID of the orders button just to make it a bit more readable. This is a result on Mind2Web cross-task split. As you can see, both methods give pretty similar results. So I guess for one, the code format isn't that like hardcore code that normal people wouldn't understand. And second, this current language models are actually pretty good at understanding both like forms of text. And the second set of experiments we do is comparing different environment representations in the workflows. So we do include environment representation for the initial state of that workflow, just for the ease of agents to recognize like which workflow applies to my current situation. Um, and by default, we use a natural language summary, basically ask the model to summarize the current web page in a short sentence. So the model may say, given that you're on the uh, like Amazon homepage, and then that would be a short description. An alternative, like a more concrete um, version of the environment is HTML code, which you have very precise like tags about like what elements are out there, which of these elements are about. And we compare like different combinations of this. The first line is the base like default setting where we only include the natural language description. The second line, we only include HTML code. And the third line, we include both. Overall, only including natural language is performs the best, at least for Mind2Web. And the main reason we observe for that is the NL caption is actually more efficient, and you actually sometimes don't need that many detail about your web page to recognize the workflows correctly. And but also this poor performance with HTML code may be due to that the current way of representing HTML is not perfect. So the entire web page HTML can be pretty long and noisy. So what we did is we used the filter method proposed by MindAct method that filters only the top relevant elements. So it only covers like less than 50% of the correct elements. And in that sense, you're not given like relevant context for 50% of the time, and it may hurt the performance. Um, yeah, I saw there's a question in the chat. Should I? Or maybe I'll go over the next slides and I'll be done. Then we'll go to the Q&A section. So this is the like also recap on our workflow memory method. We have like WebArena, Mind2Web experiments, and also a bit exploration on the workflow representations. And another set of exploration was sort of like a case study is now we're just expanding the workflow, adding the workflows into memory, but could also add those to the action space, basically turning the workflows into some functions that the model can call. And we did this a bit, and it gives slightly higher results on Web, but just we still have some issues here. For example, the environment can change quite often, quite dynamically. And the way the workflows are operating now is like we issue 4 step at time 0. And however, we're sort of assuming that we know all of the like detailed ways to take all of these 4 steps. But actually, sometimes step 3 may need some context from step the environment after action executing step 2. So may cause some issues there. But yeah, that's basically an open question. If any of you are interested in it or have thought about this, any feedback or thoughts, welcome. But yeah, overall, that's my talk.